Welcome to today's explainer. Imagine for a second if our entire Milky Way galaxy was actually a giant cosmic detector. Well, today we're unpacking a truly monumental astrophysics discovery and looking at how a global collaboration of scientists finally heard the literal background music of the universe. Okay, let's dive into this. For a long time, astrophysicists have strongly suspected that the universe isn't silent. It's actually humming with this very low frequency rumble. But what exactly is causing the entire universe to hum? And honestly, how do you even listen to a sound that travels through the very fabric of space and time? Well, this is the central mystery that teams of global astrophysicists have been relentlessly chasing for over 15 years now. Chapter 1: The Mysterious Cosmic Hum. Imagine just putting your ear directly to the floor of the universe. Teams like the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav for short, have found incredibly compelling evidence that the cosmos is filled with a persistent, ongoing background of gravitational waves. Basically, these waves are rhythmically stretching and compressing space-time itself. And by extension, all the matter embedded within it is getting stretched and squeezed as these waves wash over us. It's totally wild to think about. Now, what's really interesting about this slide is how wildly different the scale of this is from what we've seen before. Think back to 2015 when LIGO made history by detecting gravitational waves for the very first time. Those waves were like fast, extremely sharp chirps, lasting mere fractions of a second, and they were caused by relatively small stellar mass black holes colliding. But the waves we're talking about today, discovered by pulsar timing arrays, they are a slow, incredibly deep background hum. We're talking wavelengths measured in literal light years, where a single oscillation takes years or even decades to complete. Chapter 2: A Galaxy-Sized Detector. So because these low-frequency waves are just unfathomably massive, you obviously can't just build a regular metal detector on Earth to find them. You need equipment that actually scales with the waves themselves. And that brings us to the pulsar timing array. To build a detector the size of a galaxy, astronomers rely on 3 logical steps. Step 1: locate specific types of dead, rapidly spinning stars scattered across our Milky Way. Step 2: precisely track the radio pulses these stars emit. And Step 3: look for tiny correlated delays in when those pulses actually arrive here at Earth. Together, these stars act as a massive cosmic magnifying glass. And the NanoGrav team didn't just look at 1 or 2 of these stars, no way. They meticulously monitored exactly 68 of these precise flashers, using some of the absolute largest radio telescopes in the world, like the Green Bank Telescope and the Very Large Array. They watched them month after month. Some of these were tracked for up to 15 years, all just to gather enough data to prove this hum actually exists. Chapter 3: Pulsars, the Cosmic Clocks. But what exactly are these stars? Well, the answer lies in millisecond pulsars. A pulsar is basically the ultra-dense remnant core of a massive star that died in a supernova explosion, and they spin incredibly fast, literally hundreds of times every single second, sweeping these bright beams of radio waves past Earth like a giant cosmic lighthouse. What makes them so special is their sheer precision. Their pulsation rate is steady down to tenths of a millisecond. That rivals our absolute best atomic clocks right here on Earth. So, when passing gravitational waves warp the space-time between a pulsar and Earth, it messes with the signal. If a wave stretches space-time, the pulsar's radio beam has to travel just a tiny bit further, arriving slightly late. If it compresses space-time, well, the pulse arrives slightly early. We're talking about delays on the order of a millionth of a second, completely hidden beneath layers and layers of cosmic noise. Chapter 4: Ripples in Space-Time. Of course, finding a millionth of a second delay in just a single star isn't enough to prove anything. The cosmic detectives needed a very specific mathematical smoking gun to prove this background hum was real. Enter the Hellings-Downs curve. First predicted way back in 1983 based on Einstein's theory of general relativity, this curve describes a highly specific mathematical pattern, a quadrupolar signature of exactly how pulsar timing delays should match up based on their distance from each other in the sky. By checking 2,211 distinct pairs among their 68 pulsars, NanoGrav found that exact pattern. That was it. The undeniable proof that a gravitational wave background was actively washing through our galaxy. Chapter 5: Supermassive Black Hole Mergers. So, we know the hum is there, right? We've measured it. But what on Earth, or actually scratch that, what in the universe, is loud enough to vibrate the entire cosmos? Well, the leading theory firmly points to supermassive black hole binaries. When massive galaxies collide, their central black holes sink to the middle and begin to orbit one another. And there aren't just one or two of these out there. This hum is likely the overlapping chorus of hundreds of thousands of these binary pairs waltzing together throughout the entire history of the universe, sending out ripples just like pebbles tossed into a cosmic pond. And this brilliantly illustrates the sheer, mind-bending scale of what we're dealing with. To create the amplitude of the waves nanograv is seeing, these aren't your run-of-the-mill black holes. We're talking about supermassive black holes that weigh up to 10 billion times the mass of our sun. Some might even be 40 to 60 billion solar masses. It's almost impossible to wrap your head around. Now, this discovery also shines a massive spotlight on a big mystery in astrophysics known as the last parsec problem. See, when galaxies merge, black holes get to within about 3,200 light years of each other, which is called a kiloparsec. But do they just stall there forever? Or do they find a way to get incredibly close and actually merge? Well, the amplitude of the waves detected by these pulsar rays strongly suggests they don't stall. They effectively coalesce, and that produces the massive waves we're measuring today. To really ground this in the perspective of the researchers themselves, consider this observation from UC Berkeley's Dr. Luke Kelly. He said, if it is binaries, then that's the first time that we've actually confirmed that supermassive black hole binaries exist, which has been a huge puzzle for more than 50 years now. So this explainer covers data that doesn't just find a new wave, it legitimately solves half a century of astrophysical head-scratching, a real game-changer. Chapter 6. A New Astronomy Era. With this discovery, we aren't just looking at the universe anymore, we're listening to it in a completely new way. We now possess two highly distinct, completely complementary windows into the dynamics of the universe. On one hand, we've got ground-based interferometers like LIGO capturing high-frequency bursts from stellar mass collisions in the blink of an eye. On the other hand, we now have galactic-scale pulsar timing arrays monitoring low-frequency, continuous waves from the most massive objects in existence over years and decades. We get the whole shebang. So, the crucial point is that this wasn't just an isolated lucky guess by one team. No, this is a globally cross-validated discovery. Along with nanograv in North America, we saw independent datasets from the European Pulsar Timing Array, the Parkes Array in Australia, the Indian Array, and the Chinese Array. They all found evidence of this exact same background hum using the world's largest radio telescopes. The math holds up across the entire planet. Which brings us to the final, thrilling frontier of this explainer. We've built a galaxy-sized detector. We've finally heard the background hum of the universe. But what specific notes are waiting to be picked out of the cosmic orchestra next? As we refine our pulsar arrays, the next major step is isolating continuous wave detections from single, individual supermassive black hole binaries. The cosmic symphony has truly just begun, and honestly, I absolutely cannot wait to see what secrets the cosmos plays for us next.